Thank you for inviting me to this meeting, and I'm really glad to give a talk here. And I welcome everybody from Fudan University, and I hope you can enjoy these beautiful days of Kaist and Korea. Okay, this is a joint work with Taekyu Hwang. He is now in KIAS. And okay, so before I talk about symplectic capacity, I will give you some motivating examples. What are the symplectic capacities I'm talking about? Okay, so the manifold, 2n-dimensional manifold M with a symplectic structure, so M and omega be a symplectic 2n-dimensional symplectic manifold. What I mean by symplectic manifold is I have a non-degenerate closed two form omega on a real 2n-dimensional manifold. This is a symplectic manifold. Now consider R ball in 2n-dimensional R ball. So this is R ball and sitting in R2n with standard symplectic form on R2n. So standard symplectic form means dx1 dx2 plus dx2n minus 1 dx2n. So this is a standard usual symplectic form on there. Now, of course, if you just forget about symplectic structure, and if you say diffeomorphism or homeomorphism embedding, no matter how big the size of the ball is, you can always embed in a very small manifold. But since you have a symplectic structure, so the question is, because this symplectic structure is kind of rigid, a rigid property, so for what are the size of ball, does there exist a symplectic embedding of R ball inside the symplectic manifold 2n? So this is a kind of how rigid can this manifold be? Now let's consider this example. So S2 standard sphere with a symplectic form such that the volume, the integration of this symplectic form on S2 is, let's say, is pi. Now consider M to be four-dimensional manifold, which is nothing but S2 times S2 with the product symplectic form. That means sigma cross sigma. That is just, it has to be two forms. So pullback of sigma on projection to the first coordinate and plus the projection to the second coordinate. So this is a two form. Okay? And then the volume of this manifold is, this is a standard computation, this is pi squared. So the volume of S2 cross S2 is this. So there exists a symplectic embedding of radius 1 minus very small epsilon over 2 with a standard symplectic form into S2 sigma. So you can embed the ball of radius 1 minus epsilon into the standard circle, a sphere in S2. So thus we can embed B4, the 4 ball, embed into B2 of epsilon over 2 times epsilon over 2, so product, and then this one it can be embedded in M. So, if you take a limit, epsilon goes to infinity, then the volume of the ball which can be embedded, you can actually, this is an example of, concrete example where this ball can be embedded. So the volume, the maximal volume in this way is pi squared over 2. So this is a simple example. But the question is, so this is one example where the ball can be embedded in S2 cross S2 in this way. And in this way, we can show that the maximal volume is pi squared over 2. So that's by construction. But in fact, no larger ball can be symplectically embedded in S2 cross S2, i.e. there is no B4 of radius 1 plus epsilon can be embedded in M symplectically. So this proposition follows from the following theorem of Gromov. And so B2N, the R ball is symplectically embedded in 2n-dimensional manifold. That this is possible, okay? And the Gromov-Witten invariant, I will explain what the Gromov-Witten invariant is, but anyway, certain Gromov invariant is not equal to 0 for some A, then this pi r squared, so this r and then pi r squared, this value is less than or equal to omega of A. So omega of A means omega is two form, okay? And A is two-dimensional homology class. So you can evaluate this cohomology class with homology class, and then this is a real number, okay? And then this is less than or equal to this. Okay? So in fact, this simple example, so from this construction before, we have lower bound of this value, pi r squared. But on the other hand, by big theorem, by Gromov, using Gromov-Witten invariant, we have upper bound of this one. Okay. So in particular for our example, S2 cross S2, choose A. So we have to, so if there is such kind of homology class, then it's enough. So choose A to be S2 times point. And then you can see this can be Gromov invariant of this one is 1. And this WA is integration in pi. So pi r squared is less than then, hence r is less than 1. So from this example, we define what the Gromov. See, this is one of the symplectic capacity. So one of them is called Gromov width. And Gromov width of 2n-dimensional symplectic manifold, I will just say Gromov width of Gromov of M. Okay, and this is a supremum of pi r squared, where R ball with the standard symplectic form can be symplectically embedded in M2n. So how large ball can be, and why this is, okay, because this is pi r squared, but this r squared, this is not the volume of this one, but it is certainly related to this. So pi r squared, you just call it Gromov width. Okay. So in the previous example of M is S2 cross S2, we get Gromov width to be pi. So R is 1. So the lower bound is given from the construction of embedding that I gave you first, and then upper bound is given by Gromov theorem. So Gromov width is one of the symplectic capacities for symplectic manifolds, and we will discuss another symplectic capacity called Hofer-Zehnder capacity later. Okay. So some known results about the statement of some known results, and I will state the main theorem of this result. Okay, one of the famous theorem is something called the Groff non-squeezing theorem. So suppose B2 and R, so R ball is symplectically embedded into two-dimensional capital R ball times cylinder. It's a big R2n minus 1. So this is 2n dimensional open manifold. But suppose this ball, so you have a cylinder of radius R, and then if you squeeze into ball of radius R, then the Groff width of this one is pi r squared. In other words, this capital R sort of decides the volume, how big the bore can be embedded in this cylinder. So this is kind of a striking theorem. I mean, so symplectically embedding is a very rigid property. Now, actually, the Groff width, the terminology Groff width was introduced by these two people, Karshon and Tolman, and so they have another, I mean, independently by Lu. I don't know whether this person is Liu or Lu, but anyway, M is a Grassmannian manifold of k-planes in Cm. So in complex m-dimensional manifold, and you consider the collection of all complex k-dimensional subspaces, and this is called Grassmannian manifold. And okay, this is we can give UN invariant symplectic form on it, on omega. So this omega, the class, this is a symplectic form, is just two form, but you consider this as a cohomology class, two cohomology class. This cohomology class is same as the first Chern class of the manifold, which is some number times generator of second cohomology class. And then they prove that this number, M, is the Groff width of this Grassmannian manifold. Okay? So I'm going to state a similar statement about Groff width, and in order to explain the conditions, I have to give you some definitions. Of course, for the experts, this is all simple one, but there are so diverse background. So almost complex structure on a 2n-dimensional manifold. It's a manifold M with tangent space, tangent bundle, automorphism J. So almost complex structure is automorphism of tangent bundle to itself, such that J squared is minus identity. And we say this complex structure is compatible with the symplectic form. So you can give symplectic form and you can give complex structure separately, but if they are not compatible, then there's no relation. But of course, this, I mean, you know, that symplectic structure is basically motivated from complex, the imaginary part of this complex form. So this is, and also this almost complex structure comes from complex structure. So there should be some relation, and this is the relation. So J is compatible with the symplectic form if W and J, this defines a Riemannian metric. Okay? So let's say S2 with J denote the holomorphic to sphere. So S2 with the almost complex structure J, and let's say this is a holomorphic to sphere. Okay? So this almost complex structure is integrable. So this comes from complex structure. J holomorphic sphere in MJ. So we say J holomorphic sphere in MJ is a smooth map from S2J to MJ. So at this moment there is no complex structure, but let's say this is no symplectic structure, but just this almost complex structure. So S2J and M2J. So in other words, you have a complex structure here, you have a complex structure here, and then this map is, in a sense, holomorphic. So this condition is nothing but Cauchy-Riemann equation. It satisfies Cauchy-Riemann equations. So this is a J holomorphic sphere. So you have a sort of, pseudo, almost, is holomorphic mapping of S2 into the manifold. This is called the J holomorphic sphere. And almost complex manifold MJ is Fano if any non-constant J holomorphic sphere J has the positive Chern number. This is mistake. Has the positive Chern number. Okay. i.e. that means this Chern number. This is Chern number is cohomology class, second cohomology class, and U star S2. S2 is a homology, this generator, and then you evaluate this, and then this is orientation class, and so this is called Fano for any J holomorphic sphere. Okay, so the condition Fano has nothing to do with the symplectic form. It's only for complex structures, almost complex structures. But since we are working on symplectic form, symplectic structures, a symplectic manifold with a symplectic action on a circle, action of a group G is Fano. We say there exists a omega compatible G invariant almost complex structure J such that M and J is Fano. So this is only, we are considering symplectic structure with a symplectic action of Lie groups. So it has, this is only.
In this case, the Chern number, just equivalent Chern number is ordinary.
No, ordinary Chern number. Oh, yeah, that does not have anything to do. Yeah, ordinary Chern number. Yes. Okay. And we say, so from now on, I'm going to consider the action of circle, S1 action. So the circle action on symplectic manifold is called the Hamiltonian if omega is S1 invariant. So this is a S1 invariant, and the contraction of this omega with this x is minus dh. That means, so this, there is a, for some smooth function h, m to r1, where x is the fundamental vector field of S1 action. So if S1 is acting, then if you choose one point by S1 action, you have an orbit. And in this one, by considering that, you have a vector field on it. And this vector field is the fundamental vector field of x. And omega is two form. The contraction of x, ix is omega, and you put one value in x. So it becomes one form. And this one form is same as derivative of the h, so the one form this. And this is called the Hamiltonian action. And then h is called the moment map of this action. Okay, so from a manifold, so the moment map is h is, from this manifold you have a function from m to r, okay? And so H max is a maximal critical value of H. So you have it's like a Morse function. So you have a manifold sending the H sending to real number, and then you have critical values, and then maximum value, critical value, I'll say H maximum. And F maximum means maximal critical value, the inverse image. And HS max means the second maximal critical value of X. So you have a critical maximal critical value and the second maximal critical value, okay? And then critical values are discrete. And H minimum is the minimal critical value. So I'm going to consider manifold, close the manifold. So the image has to be compact. So you have a maximum and minimum. And then in the middle you have several critical values, but I'll just write that way. Okay, so this is the statement of this symplectic capacity, or rather Groff width. So MW is a closed, and circle S1 is acting on it in a symplectic Hamiltonian way. But one more condition is the action is semi-free. So the semi-free action means if it has fixed points, and otherwise, except for the fixed point, all the action should be free. So the isotropy subgroup of this action either S1 or trivial. There is no other finite subgroup isotropy group at all. Okay. Okay. In this, and moreover, I need one more condition, that F maximum. So you have a maximum critical value, and the inverse image has just one point. So in other words, this manifold has to be something like going down, okay? Going down, and then you have only one maximal fixed point here.
That means fixed point size contains isolated fixed point.
Yes, yes. But not only that, but it has to be the maximal value. Yeah, it is isolated. Oh, later part you may have many components, but the maximal is just 1 point. Okay. The reason why I require 1 point is from this maximal point, and the next critical level, I'm going to embed sphere, or not the ball, our ball. Okay, that's what I'm going to. And then, in other words, in fact, the Groff width is h, the value h maximum, and h second maximum, the difference. That's the Groff width. Okay. So in other words, in a sense, you have a maximum one fixed point, maximum fixed point, and then the manifold goes down, and then this part looks like ball. It's kind of geometrically feasible, but anyway. Okay. I don't think I have enough time to talk about Hofer-Zehnder capacity. It is some slightly different capacity, but I don't think that the way it is proved or statement is quite similar. So anyway, there is another called the Hofer-Zehnder capacity, and by the same condition, I will say in this case the same condition, but Hofer-Zehnder capacity is from H maximum to H minimum. That's Hofer-Zehnder capacity. So I'm not going to talk about what is Hofer-Zehnder capacity, but the value is this. Okay. Okay, so let me give you an example. Several examples. Okay, Kaist and Tolman gave a result on Groff width on Grassmannian manifold, and using our result, we can get it rather easily, or we can reconfirm their result. So M is Groff, Grassmannian Km, and for simplicity, we may assume that K is less than M minus K. It doesn't matter, right? Because M minus K, if instead of K you said M minus K, they are equivalent. So let omega be W UN invariant symplectic form, and then such that omega, this class, is same as M times generator. Now consider S1 action on CM. By the way, this Groff width has nothing to do with group actions. Right? This definition has nothing to do with group action, but the Groff width is very difficult to calculate, to compute. So I just add some action in it, and the condition that if this one has some nice symmetry, then we could calculate this capacity. This is what I'm going to say. So let's introduce the Hamiltonian circle action on on Grassmannian manifold as follows. So consider S1 action on Cm, complex n-dimensional, with a simple multiplication on the first k factors by multiplying by complex numbers. So T is a circle element, group element, and then this is Cm, and then you can just... And then it induces a semifree Hamiltonian S1 action on a Fano, in fact monotone. I'm not going to talk about it. But anyway, this manifold is Fano, and it is a S1 action, Hamiltonian S1 action. So what we have to do is we have to calculate all this H maximum, H second maximum, and so on and so on. So in order to do that, what I do is you decompose Cm into the first k factor times 0 plus 0 times Cm minus k, like a V1 plus V2. And so the fixed point of this manifold correspond to, so the element in Grassmannian manifold is k-dimensional subspace, right? So this k-dimensional subspace, but I decompose this 2m-dimensional manifold into k-dimensional subspace, m minus k-dimensional subspace, and the fixed point set the corresponding to the k-dimensional manifold space can be some different space, right? So it's an invariant subspace W. So any V in W can be such V1 plus V2, where V1 is V1 intersection W and V2 is... This is just a simple linear algebra. So W is a product of subspace of V1 and V2. So W is a subspace of V1, product of V1 and V2. So so any S1 fixed point component of M is in this form. So any fixed point component is, you can check it. It's very simple one, okay? And so decompose the tangent space of this Grassmannian manifold at this fixed point. You can decompose this is equivalent to the tangent space. I mean, you can check it, Grassmannian manifold. And then, okay, this is a simple computation, but all I need is, so the tangent space of the manifold, this is tangent space of the manifold, and it can decompose into 4 different pieces, 4 different parts. And so because this a tangent space of fixed point, you have a circle action. So this is a S1 representation. Okay, so S1 representation decomposes into the weight numbers, right? So S1 weight of the first, so I have four different parts, and the first and fourth, they are weight 0. So that means they are fixed part. And the second term is weight minus 1, and third term is weight plus 1. You can check it. It's a very simple computation. And by a result of Macduff and Tolman, we know that for each fixed point component, F, its moment map image is nothing but the summation of their S1 weights at the fixed point. And we have calculated, we have decomposed in the tangent space of the fixed point. So hence, for a fixed component F of this form, and I have decomposed tangent space of this into 4 different pieces, and then second and third are weight minus 1 and plus 1, and the others are 0. So from this computation there, and then from this summation of weight, you know the image of this moment map, you know exactly, you can calculate this. So H maximum, H second maximum, H minimum is it can be calculated this way. And H maximum occurs when K1 is K, and minimum occurs when K1 is 0. So Groff width is exactly H maximum minus H second maximum, which is M. And Hopper agenda is this one minus this one, which is Km. So this conforms the result of Kaist and Torman. Okay. And also we can do the similar work for product of symplectic Fano manifolds, where but in the case when Hi maximum, so this is the condition, this maximal part consists of just one single point. So each vector satisfies the condition on our previous result, and then product of this manifold, then their Groff width is nothing but the minimum of this capacity. And the reason is that the moment map is summation of moment maps of each vectors, and then the H maximum, second maximum occurs when this difference is the smallest. So
also the semi-free,
oh sure, not semi-simple, semi-free. Thank you very much. This is mistake. I've been trying to check it, but it happens all the time. Thank you very much. This is semi-free, not I don't know what is semi-simple Hamiltonian. Yeah. And another thing is a blow-up. So this is a Hilbert surface. Okay. So Hilbert surface, and Hilbert surface is toric manifold, and at a fixed point, and you may choose the size of blow so that M is monotone, and that means it satisfies Fano condition. And the moment map image of this manifold blow up is like this. Okay, it's a polytope.
This the action is not semi-free. It's just the orbit space is this polygon.
No, I'm not. This is toric. This is T2 action.
T2.
I'm going to restrict it to circle action. So, yeah, that's a good point. And here, assumption semi-free is needed. So the toric, this is not semi-free. Good point. But this is T2 action. Now I'm going to restrict the circle action. So two different circle actions. One is semi-free, one is not semi-free, and the semi-free satisfies the condition, but not semi-free does not satisfy the condition. That's what I'm going to talk about in this. Okay? Good that there is some person who is actually following. Okay, so this is, so the moment map is from if you have a Lie group, Hamiltonian Lie group action, then the moment map is a map from the manifold to the dual of Lie algebra of the acting group. So S2 is Lie algebra. So you may consider that dual, it's R2. So this moment map is a map from manifold to R2. And this image, this one is sitting in R2. So now I'm going to restrict this action to two different circle actions. One is generated by phi1, then that means forget about first S1 action, but only the second S1 action. And then next phi2 is you have circle action which is generated by -1 and -2, -1 and -2. So you have a sort of diagonal action. Not exactly diagonal, but the slope is 2 diagonal action. So in this case, T2 weight at the fixed points are just outward primary vector from the corresponding vertex. So outward, so it goes to this, and this vectors. They are T2 weights of this action. So for a real relatively prime AB defines a subcircle action induced by the inclusion S1. S1 is included S1 times S1 by this way, T to the A, T to the B. Then S1 weight at a fixed point is T2 weight inner product, dot product AB. So we consider the following 2 subcircle actions. That's what I mentioned before. And then I calculated for the first phi1 action, and you can check this phi1 action is semi-free. And then weights at the fixed points are, okay, this is simple computation, and I'm not going to discuss this. And I gave you all these details, how to calculate this weight. So at this one, weight is, at the fixed point is this, and the H maximum is 2, H second maximum is 0, H minimum is -1. So Groff width is 2 minus 0 is 2, and Hofer-Zehnder capacity is 2 plus 1 is 3. But if you consider phi2 action, which is not semi-free, then you have different values. You have H2 is 2, H2 second maximum is 1, and is -3. So in this case, H2 maximum minus H2 second maximum is 1, which is not equal to 2, and then so action is not 3. So this is what we have. Now, how many?
10 minutes.
10 minutes. So this is, I don't know whether it's, okay, you can see. Okay, so as I said, the lower bound of this Groff width is, lower bound is how you just actually construct this embedding. So if you actually embed this split embedding, then at least the supremum should be greater than or equal to that. So that gives you lower bound. Okay, so lower bound can be, and in our case, this computation was done by Kaist and Tolman, and we do the same, exactly same computation in our case, and then we can see Groff width is greater than this. So we can actually construct an embedding of this size. An upper bound is, as we apply Groff theorem. So if Groff written invariant of certain A and certain alpha, if we find Groff written invariant is non-zero, then we are done. So we actually have to calculate some case where the Groff written invariant is not equal to 0. Okay, there are infinitely so many Groff written invariants. So what's the big deal of finding something which is not 0? Well, Groff written invariant is very difficult to calculate, and that's the problem. So what we are going to do is we will prove that Groff written invariant of M with A 3 point alpha to alpha 3 is not equal to 0 for some A and alpha. Okay, so let me just give you brief idea what the Groff-Witt invariant for the people who do not know the terminology. Okay, so Groff-Witt invariant, as I said, M omega J is a 2n-dimensional symplectic manifold with omega compatible almost complex structure J. And I said we are going to consider genus zero surface, that means sphere. So I only consider the holomorphic image of a circle and a sphere. But also, of course, Groff-Witt invariant for different genus is also defined. Okay. So S2J is a two-sphere. S2 is a P1 with complex structure J. So fix a homology class A, and let alpha 1 to alpha k be cohomology class with Q coefficients. Okay. Groff-Witt invariant roughly means it's number of J holomorphic spheres. So how many S2J can be mapped into manifold J holomorphically, such that it has an intersection with these cohomology classes. So what do you mean by cohomology classes? You think about Poincare dual. And the Poincare dual is homology class. So homology class, every homology class by itself is not represented by submanifolds, but if you multiply by subnumber, then it can be represented by manifolds. So basically, you have these cohomology classes. Then you can replace this by some submanifolds. So you have some manifolds, and you have the sphere image, and then how many maps you can embed, maps into, so that its image has intersection with all these submanifolds. Okay, and why? And this, so cohomology class is not represented by manifold, but some number multiply, then it is generated. That's why we have to consider Q coefficients. So it is not, intersection number should be integers, but you have to divide by this multiplying some numbers. So that's why you have to consider only in Q coefficients. Okay, so this is a signed number. So sign means intersection in orientation considering, and the plus or minus. So this is what we have, okay? And if this one, the degree does not match, then of course you can miss everything. So you have to have nice degree matching. So this is the condition. But anyway, basically how many, so the Groff-Witt invariant is a signed number of J holomorphic spheres whose image intersects with the cycles representing the homology class, this one and this one, and if this one, and otherwise it's zero. Okay. Now, in order to calculate Groff-Witt invariant, see, what we do is we consider quantum cohomology. And the quantum cohomology, it's all these coefficients has information about Groff-Witt invariant. And then by looking at certain element multiplying in there and do some computations, you could find some non-zero elements. And this multiplying by something, this multiplying element, something called the Seidel element. But so that's why I need to explain quantum cohomology and the Seidel elements, but this is quite involved. And I think for this lecture, I better not discuss more about that. But if you are more interested in that, I will give you my slides so you can get it, and then This is sort of some crash course for the quantum cohomology. Anyway, I think I should stop here.